I'm very sick of and ask questions if you have trouble with any of the labs. Please ask questions. So, and just remember for you guys over in Enid, I have a 2:30 meeting. So the lab will be set up, and I think there'll even be some folks in the room by then, so that will help you as well. All right. So this is, I'm going to go ahead and do a slideshow. So we on Friday, we started talking about sound and waves in general. And the chapter we're working with in your text, if you want to go back to the chapter in the text, is chapter 14. So we're covering chapter 14, and we're going to look at things like the Doppler effect and those kinds of things. So we talked about this on Friday. I have two types of waves. I have a transverse wave, and I have a longitudinal wave. Slinky can demonstrate both of them. The transverse wave is going to be up and down, and my longitudinal wave will have what we call an area of compression and an area of rarefication. So we can see that moves through, and this is a sound wave. A sound wave is a longitudinal wave. It's going to, and both of these two waves here, as we're demonstrating, require a medium. Can be a string, can be a slinky, can be air, can be water, can be a lot of different things. So we talked about the speed of a wave. The velocity is going to equal the frequency times the wavelength. And that was one of the things we covered on Friday. If I have an electromagnetic wave, like a radio wave or a light wave, or something that is going to be on our spectrum, like a microwave, the speed is going to be the speed of light. But for mechanical waves that require a medium, electromagnetic wave is special, but for a mechanical wave that requires a medium, that's going to be the velocity is equal to the frequency times the wavelength. And that is going to be dependent on the medium. Okay? And it's distance divided by time. Velocity is distance divided by time, just so when you're doing your speed of sound lab, it's the distance that the wave traveled from the snap to the end of the tube and back, divided by the change in time. Pretty straightforward. And we're using it for all kinds of waves. We talked about constructive and destructive interference. That's why I can have noise canceling headphones. I can be in different spaces. And if I'm looking at a tuning fork, you can kind of see that vibration of the tuning fork, which is causing the increase in density of the air as it vibrates. And then as it comes back inside, it's going to, we're going to see a less of the density of the air. So we had an area of compression and an area of what we call rarefication. So when we're thinking about sound, we're seeing a change in density. If I'm dealing with a string, we're playing with tension in the string, and we're working with it. So there is where I have my rarefication and my other. So if I go over here, and we can actually play with a little GIF that shows that lovely little piece, that you can see the compression and compaction and rarefication. But like what we saw last Friday, I can describe that density as a sine wave. which is why we started with simple harmonic motion. So when we jump into sound, and it turns out, I told you guys that we can look at our sine wave in terms of distance and time. Well, when I went back and looked at you guys' textbook, you guys don't have the kx or the omega t kx equations. We just jump right into sound. So you guys got lucky. You don't have to mess with that one. I do that for my engineering physics folks, but not you guys. So when we deal with sound, it's just like our eyesight. You know, when there's a visible range of light, we have visible light. Our ear has a certain range. Now, what's really cool is the dynamic range that we hear. So sound for a human ear, a normal human ear, is 20 hertz to 20,000 hertz. So think about the orders of magnitude that we're dealing with. 20 hertz to 20,000 hertz. And yes, there are people that can hear above that, and there are people that can hear below that. But that is our normal human ear. Infrasonic are frequencies below the audible range. Elephants live in the infrasonic area. Earthquakes, which is also interesting because sometimes you can hear earthquakes. Depending on what type of earthquake you have. I used to live in Salt Lake City, or just outside of Salt Lake City, and our basement was built into the mountainside. So it was very rocky, and you have rocks. And we would hear one room in where my son used to sleep when he was a little guy. You would hear this moan come out of the room. And I'd go check on my son, and he was fine. And you'd go in, and periodically you would have this happen over and over again. Well, it turns out it correlated very nicely with earthquakes that were happening up in the Yellowstone region. They were traveling down the mountain, and that room just happened to resonate, and you would hear the room act like an echo chamber. It was kind of an interesting thing. And those things happen. Ultrasonic waves are frequencies above the audible range. Dog whistles. You know, something that's above 20,000 hertz. And if anybody's ever had an audiogram done, you'll also know that even though normal hearing is between 20 and 20,000, we have a couple of places where we have gaps naturally. There's a couple of areas where we have some natural frequency gaps. So the human ear is a varied piece. So if I'm thinking about a string, and we've all done this, right? If you play a stringed instrument like a guitar, or we've all made that little funky guitar. If I tighten a string and I change the tension in my string, I'm going to get a different kind of a sound, right? The more tension I have in it, the higher what we are going to call pitch. So when we describe sound, we use terms like pitch, we use terms like color, we use a variety of different terms to describe how that sound comes across. But basically, if I have that string, the velocity is going to be dependent on either the tension of the string or what we call the elastic property. So steel is going to have a different elastic property than air, which is going to have a different elastic property than oil. All of those have different elastic property, and it's an inertial property. So if we're thinking about how sound or a sound wave moves, it's carrying energy, and it's a series of collisions, right? That air, as it increases the density, it's pushing on its neighbor. It's getting us out there. So if we look at this, we can, if I'm dealing with a material like water or steel or air, it's compressible and it has a bulk modulus. And then we also have its density, and we can compare for that transverse wave on a string. And that also relates back to the tension versus the length. I think in your homework, you have a couple of problems that deal with this. I have put that in your homework so you can see how it works. That's in there. But I am not going to test you over this. Okay? You will have to know how to calculate the speed of a wave if I give you wavelength and frequency. Or if I give you the speed and, and the frequency, you have to calculate the wavelength. You will have to use that one, but this would not show up on a test. Now, this is for those of you who are sonographers, looking at how you're going to be dealing with x-rays and things like that. This is why you can see different tissues, because different tissues are going to have different elastic properties than other things. And it's going to characterize the material quite a bit. For example, if you have a bump in your arm, they can kind of tell you, is it just a cyst of some sort? Because it might be a water-filled or a pus-filled cyst. Or if it's a calcium nodule, or if I have a dog, it could be a fat nodule. And it's because fat is going to echo sound or react to sound differently than calcium, a calcium deposit would, or a liquid deposit would. So they can act, you can use sonograms to see kidney stones, and you can use sound waves to break up a kidney stone, right? Because we know if I hit just the nice resonance, I can actually break up something. So this is one of the reasons why we can do that kind of medical devices. So we can look at that. And like I said, you've got a couple of homework problems, but I don't test over this. This is not something I test over. And if I have a rod, I can use Young's modulus. If I have a string, I can use tension. It's just dependent on what's keeping the wave out there. So in your laboratory, the laboratory write-up, it gives you one way to convert the speed of sound in air based on temperature. And here's another way. You've got the speed of sound in dry air is 331 meters per second. So at room temperature, which is around 72 degrees Fahrenheit, how we normally deal with it, or 20 degrees C, the speed of sound is going to be around 343 meters per second. Now, we're only going to correct for temperature. But you can probably anticipate that humidity may also impact how sound travels, because the speed of sound in water is different. So that's one other thing. And we all know that on a crisp, cool morning, on a real crisp with, real dry, cold, sound travels really clearly. We don't lose a whole lot. We also know that the wind is going to disrupt our sound wave. So we have a lot of different things that impact how we hear something. So, sound is not only speed. How we hear is going to be based on the intensity or the strength. And this is where we're going to get that idea that it's going to fall off as 1 over r squared. So if I'm right next to my speaker, I'm going to have a different intensity than if I'm across the room from my speaker. And we know this because if I'm dealing with a bass speaker and I'm sending right next to it, my fillings vibrate. You can feel it all the way through you. But if I'm across the room, I don't get that same sensation. So it's going to drop off as 1 over R². So we're going to define intensity as a power or change in energy with respect to time. So waves carry energy, so I can look at the power of that. So it's the power per unit area. So whatever that power is, that change in energy per unit time divided by the area. The SI units for intensity for sound are in Webers per meter squared. Now that's typically not how we measure sound. And the reason we don't measure sound that way, intensity, is because that's hard to work with. And you'll see that here in just a second. And therefore, we end up using the unit of decibels, and that's a logarithmic unit. So I would encourage you to go back and look at the appendix in the text and refresh your memory on how to manipulate logarithms. I think I have put in Blackboard and some of the example problems how to work with logarithms, because you got to kind of remember how to do it. We haven't done it in a long time, and working with logarithms is where we're going to be with decibels. So you want to be able to look at that. So it's power per unit area. The threshold of hearing, what our ears are designed to pick up, is 1 times 10 to the minus 12 Webers per meter squared. 1 times 10 to the minus 12. Let's see let's see what my animations are. Yep. That's probably a flash player. That needs to be fixed. What causes us pain is 1 Weber per meter squared. 12 orders of magnitude is how sensitive our ears are. So it's a very sensitive detector, an extremely sensitive detector. And we can detect pressure fluctuations as small as about 3 parts in 10 to the 10th. Which kind of leads to why we have to worry about our hearing so much. If I live in a very, very quiet environment, and that's one of the things that they notice in some of the Alaskan communities, where people live in a very quiet environment, and then they fire off a rifle, that sudden jolt to their ears is enough to cause permanent damage. So that's an explosion. If you're standing right next to an explosion, you're going to ultimately, you can damage your hearing. OSHA deals with time-weighted averages because they don't want you to be exposed to high levels of noise, because it will ultimately damage your hearing. So it's all related to the fact that we have a very sensitive item there. Because of that range is why we got to use logarithms. We've got to use logarithms because we're working with 12 orders of magnitude, and the only way to have any kind of semblance of that is by working with logarithms. So we're going to define the decibel. And the decibel is equal to 10 log 10, the intensity of the sound, divided by our normal threshold of hearing. So that's going to be that. If I go back here, that's going to be my 1 times 10 to the minus 12 is what I'm going to put in the bottom of this equation. So intensity is the physical quantity, and we use this as a convenient way of dealing with it, because you'll notice that's a ratio. And so decibels deal with that ratio. And it's just a nice way to be able to handle it. So if I think about our normal environment that we deal with, a quiet office sits at about 40 decibels. Your rock concerts, your symphony orchestras, up in, jet aircraft. There are a lot of different things. You can go in and find all kinds of these intensity scales all over the place. But this is the one thing that you want to look at is where OSHA regulates. And OSHA regulates that if you're in a work environment where there's over 90 decibels, that you have to have a hearing protection program in place. You have to have an action level at 85 decibels. So if I'm standing right next to a pump, a compressor, a generator, a loud piece of equipment, and I have somebody that's standing right next to me, if I have to raise my voice in order to be heard over that equipment, you're probably right at 85 decibels. That's a nice rule of thumb that says I'm at 85 decibels. If I'm within 3 feet of that piece of equipment and I have to raise my voice in order to be heard over the equipment, I'm at over 85 decibels and I should have on hearing protection. Lawnmowers, ATVs, motorcycles, all of those things are over 85 decibels, folks. And all of those can have the potential to damage hearing. And we worry about that on an 8-hour time weighted scale, just so you guys know. It's an 8-hour time weighted scale, which is also why a lot of people worry about having the earbuds, earphones, all of those things, because you're putting all of that right next to your ear and it's a sensitive piece of equipment. So you don't want to lose hearing over that. And as we age, we will naturally lose some of our hearing. But if we've worked in a noisy environment, we're going to lose it faster. If we've had some sort of an accident or near an explosion, odds are we're going to lose some of our hearing there. But that's one of the things that you definitely have to worry about. So this is how it works. If I start out with a trumpet that's at 75 decibels and I want to add 4 more trumpets, it's not 4 times 75. And it doesn't work that way because we're working with logarithms. So what I'm going to do is if I have 4 trumpets, I'm going to multiply the intensity times my 4 trumpets because that's the physical quantity. Right? That's my physical quantity that I'm dealing with. And if I go back into my appendix, if I do log of A times B, I can separate log A plus log B, and I can separate that out. So now I've got 10 log 4 plus 10 log I over its intensity, which we were told in this case was 75 decibels. 4 trumpets are now at 81 decibels because of how I'm going to do and deal with the logarithms. Yes, on the test, you will have a problem looking at if I have, if we have a crying baby and we've got 4 crying babies now, what's the sound, how is the sound level going to increase? You will also probably have a problem that looks like if something has an intensity of 1 times 10 to the 8th or minus 8th, what is the decibel for that sound? Or vice versa. What's the actual intensity if I have a jet aircraft at 100 decibels, which is a little low for a jet aircraft. Okay, so those are kinds of problems that you will see on the test associated with decibels. And this is how you would do that calculation. You know, if I'm trying to find, doing the reverse, if I'm trying to find the decibel level and vice versa. So go back and review logarithms. These aren't hard, we just haven't done them in a while. You know, we just haven't done them in a while. We talked about spherical waves. And so this is where we get the idea that the intensity is going to fall off as 1 over r squared. If I have my power divided by area, the air surface area of a sphere is 4 pi r squared. So as I move away, it's going to fall off as 1 over r squared. And so you can do that relationship there. What's my intensity as I go back and forth? So this gets us right into the lab that you guys are doing. Gets us right into the lab that you're doing. So we talked about this on Friday. We're going to use rays to describe wave fronts. And now I have some better pictures than what I was actually drawing on the sheet. And I can look at plane segments, and we can look at waves kind of going off as planes. Again, pretty much what we talked about. So do I have any questions so far? Everybody good? Everybody still awake? All right. So let's talk about the Doppler effect. We all know the Doppler effect. We've all heard it. We've heard the siren. We've heard the train go by. You all heard that the London subway system, they had to reroute and cancel 14 different lines. Yesterday, I think it was yesterday or the day before. No, it had to have been yesterday because it was during rush hour. The London subways were stopped because a swan was sitting on the tracks. I don't know if you guys are familiar, but in England, all swans are owned by the crown, and you can't hurt them. And they're like protected species, like eagles are here. And so the swan stopped all the traffic. It was kind of, I heard that news story this morning. It's kind of like, I like hearing those odd news stories. But we've all sat next to the train. We've all sat next to heard the siren come in. And we know as it's approaching, and because we know about the Doppler effect, we know whether the car is approaching us or the car is moving away from us. What's fun is we typically think of the Doppler effect with a high-pitched sound, like a siren. Well, on a crisp, cold day, you can hear the Doppler effect with a goose honk. It's kind of fun. You know, you can hear it with vacuum cleaners, vacuum tubes. One of the ways that you can demonstrate it, and I'm sure everybody's played with one of those whirly tubes. You can play with a whirly tube and hear the Doppler effect. So we can hear the Doppler effect, and the Doppler effect works for all waves. It doesn't matter if it's a sound wave or an electromagnetic wave. This is how we know we have an expanding universe. This is how we can tell that certain stars are moving away from us, because their color is shifted. And so we can actually utilize this in a number of ways. So the Doppler effect is affected by, we can either have the source moving, the siren on the car, and the car's moving down the road, or I can have the siren sitting right in one spot, and I can have the Doppler effect as I am moving towards it or away from it. So it's that relative motion between the source and the observer or the hearer. Okay? We do have to make a couple of assumptions. One, that air is stationary. And for most of what we're doing. And all speed measurements are made relative to the stationary medium. So if I'm on the train or I'm in the car that's got the siren, I'm not going to hear the Doppler effect because I'm traveling at the same speed as the source of the sound. That's why on a train, if I'm sitting on the train, I do not hear a change in the horn as the horn is blaring. But if I'm standing outside at the corner as the train goes by, I'm going to hear it. So basically, this is what's going on. So this one, I have a stationary source. It's not moving. It's producing a sound at a certain frequency and wavelength. My observer is coming in and it's going to hit that first wavefront. But it's going to hit the second wavefront sooner than it would be if I were just standing there. Because I'm going to be coming into that second wavefront sooner than I would be standing there. Now, if I do it the other way and I'm moving away from that wavefront, so it's going to take that wavefront a little longer to catch up. So I'm going to have a bigger gap in terms of, so it's going to be a little bit of a perception problem. Let's see if I got this one will work. Maybe. Here we go. So here, let's see if we can get there. We got the example of the Doppler effect. So that's what we're all familiar with. And this is an animation that shows there's my source moving, and look at how the wave front is changing. It's still sending out the pulse on an even time, but those wave fronts get compressed because the source is moving at a certain speed, and it's, even though those waves are out there, so it's tightening it up. Now, as I'm moving away, the gaps are getting longer and longer and longer. So that was a moving source. So you can see the differences there. So this is a moving observer. So you can kind of play with that. Let's see, that's observer approaching and receding. Where's my other one? So there's the other one. So there's the fixed source, and you can see the fixed source, and the person is seeing it and is going to see that wave compressed. And now you're seeing how it's slower on the other side. So we have some fun pieces there. So this is a handy, to be able to see it a little bit. So we have if the moving away from the source, the frequency is going to appear lower. If I'm moving towards the source, the frequency is going to appear faster. And that's if the source is stationary. And if I do that, this is how I have it. Now, I will tell you guys, it is very helpful to keep the 3 Doppler effect equations there. I tell you, every time I do Doppler effect problems, I have to sit and ponder it for a second, because inevitably you're going to get the source and the observer reversed. And you have to make sure you've got it straight in terms of what's happening. So this one is if the stationary source is fixed and the observed frequency is out there. So you will have this for our stationary source and a moving observer. Typically we use S to represent the source, and we use O to represent the observer. Then we got the reverse, okay? I got the reverse where the source is going to be moving. And when I do that, this is how the equation works out. And then you have the general equation where both the source and the observer could be moving, which I'll show here in just a second. I'll give you a chance to write something down. And it still seems to be recording, so we're in good shape today. Seems to be recording, we're in good shape today. And that's the general equation that has both the source and the observer. And you may have to play with it a couple of times. And yes, there will be a Doppler effect equation on the exam. So you know you're going to have at least 2 decibel equations. You know you're going to have calculate the wavelength or the frequency or the speed question. You know you're going to have a Doppler effect question. Good? I'm still writing. Yep, good. All right. All right. The Doppler effect does not depend on distance. That's that's why we can do stars. That's why we out there. It doesn't depend on distance. Now, distance though will affect the intensity. All right. Distance will affect the intensity because we know that the intensity falls off as 1 over r squared. So when you do your Doppler effect lab, you'll want to make sure to take that, but the apparent frequency will not change. So I'm going to stop right there. Questions on the Doppler effect? All right. Because this is when we started looking at if I am the source and I am moving, and all of us, and we know what's happening is we're compressing those waves, right? Waves carry energy. I'm compressing those waves. So think for a second what's going to happen when my object starts moving faster than the speed of sound in the medium. I'm going to overtake my wavefront. If Fundamentally, that's what's going to happen. I'm going to overtake my wavefront. And it's not until Chuck Yeager happened that actually had that work, that we knew what was going to really happen or what the impact was going to be on the human body or the aircraft. Now, we've had things go faster than the speed of sound, and each one of us can actually have something go faster than the speed of sound. The end of a whip, that crack that you hear with a snap of a whip, that is faster than the speed of sound. Now, granted, we've only got a little bit of it thing there, and we're not going to get a good boom. Most of us in Oklahoma have heard sonic booms before. You didn't necessarily know that that's what it was, because we have had aircraft fly over us greater than the speed of sound. They're not supposed to, but they have. I'll tell you for sure, certain, that we've had SR-71s land either at Tinker or the Air Force Base over in Enid, or the one down in Altus. We've had SR-71s land because the paint manufacturer for the SR-71 came out of Tulsa, by the way. The people that actually made the paint for that stuff. And the SR-71 is a unique aircraft. Nobody really knows how fast it can go because they've never let it all the way out. That was kind of a fun story. We had a guy come in and talk to us about the SR-71. And basically, every time the Soviets would break the record, they'd go and fly the SR-71 and let it out a little bit more. So we've experienced sonic booms. We know that that happens, and that particular cone is a shockwave cone, and we know that shockwaves, we can see them, we know how they react, we can do a lot of different things with shockwaves. And you can get that angle of the cone depending on your velocities and the Mach numbers that are out there. And if you really want to have fun, you can go out on the internet and look at shockwaves. They're like everywhere. You can see different planes. What's interesting is this one up here. It's usually their air speed monitor. They have a little pitot tube that's up there to help them see their air, and that point will usually also generate a shockwave. And if you've got just the right vapor conditions in the atmosphere, that shockwave will cause the water vapor to condense right away, and you can actually see the cones. And they're pretty spectacular. And you can lose yourself for hours on the internet looking at the different cones that are available. But if I'm in the plane, I don't hear the sonic boom. And the volcano that erupted last week, that's what people heard in Alaska was the sonic boom. That's what they actually heard, was the boom when that volcano went up. So, little tidbits. All right. So now we're going to start dealing with music and standing waves and different aspects there. So we know that waves can have constructive and destructive interference. I can set up a standing wave, and this is what we're going to get into in terms of resonance. A standing wave is going to give me resonance. If I'm in a string, I'm going to set up a standing wave in the string, and we're going to talk about nodes and antinodes. And I get constructive interference at regular intervals. And that's going to be that N number that we're dealing with. So I'm going to get constructive interference when the two waves interact at some whole number on the wavelength. I get destructive interference when I'm at half. So it's going to be 1.5, 2.5, 3.5. N is going to be an integer. And I'm going to create a standing wave. And I'm going to go over here. So when I do this, this picture's, okay, it's actually showing through the screen a lot better. When I get a vibrating string, I can set up, and if I've got just the right length and tension and vibration, I can set up a standing wave in my string. I can also, and we know, and we've done this, everybody's blown across the top of a bottle. You're setting up a resonance, you're setting up a standing wave inside your Coke bottle. You can do it in a glass. We can make glasses sing, right? We can do it in a glass. We can do it in a string. We can do it in an organ pipe. We can do it inside a flute. We're setting up a standing wave. Now, this one has 1.5 wavelengths in it. The point where I'm getting destructive interference, so it's going to where the wave appears to be still, is called a node, and the open part is called an antinode. So my node is right here. This is my antinode. So if I have a string, the first standing wave that I can put into this string would be having a node here and a node there, or half a wavelength. So I'm going to have a fundamental frequency where I'm going to be able to set up a half a wavelength. And that's where we're going to be. So this is a full wavelength. And what we're seeing is these are going in there so I can actually have my amplitudes differ. So if I have a length here, here's my fundamental or my first harmonic. This is my second harmonic. This is my third harmonic. Now, what I'm likely to do on a test, rather than have you calculate them, I'm likely having you draw them. So if I'm in a string, I'm going to have to make sure that I have my nodes are at the fixed points. And this will give me my fundamental frequency. This is going to give me my fundamental frequency. So I'm going to get my standing waves. And we can do forced vibrations, which get them to actually get up there and swing them better. If I have a tube, and I can have my tube open at both ends, I have to make sure there are antinodes at the ends of the tubes. I have to have antinodes at the ends of the tubes in order to get that resonant frequency. So it turns out, again, my first harmonic is a half a wavelength, where I have an antinode at each end of the tube. And then I can increase my harmonics as I move up. But if I do organ pipes, I've got a closed end, which is going to have a node at the closed end. And I'm going to have an antinode at the open end. So I'm at 1/4 of my wavelength for closed pipe, for one side being closed, one side being open. But that's why I can change a pitch, because pitch is generally related to frequency. Pitch is generally related to frequency. I can change my frequency, increase my pitch, and go from a middle C up 1 octave, up a 2nd octave. What I'm doing is I'm setting up a different resonant in there. Okay, and you can do that one. All right. So let's talk musical terms for a little bit. I will tell you it took me forever to be able to hear a beat. I am not necessarily musically talented. So for me to hear a beat was very difficult. If you've got two frequency generators and you set one at 600 hertz and you set the other at like 605 hertz, you're likely to hear a wah, 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 wah in the sound. I used to do a lab with this, but I couldn't hear them well enough to be able to help anybody do it, so that's why we don't do a beats lab. If I can't hear it, I'm not gonna force anybody in it. But for those of you who are musically inclined, and those of you who have two flutes sitting next to each other and you know they're not quite in tune, will tend to hear the part out, and you know they're off. That is something called a beat, okay? And it's related to the loudness. It's because something's very, very close in frequency, but we're not going to get there, and they're going to have slightly different frequencies, and you're going to hear it. So pitch is sort of related to frequency. Beats are a result of being sort of just outside off. And we talk about timbre in sound. It's Timbre, timbre. And so if I play a concert A on a violin, if you've ever gone to the symphony and you've heard them tune the instruments, the violin is going to play, the concertmaster violin, first chair violin will play a concert A. And when you hear that violin play the concert A, you know it's a violin. The oboe on the wind section is also going to play a concert A so that the woodwinds can tune in on that concert A. Now that concert A is a specified frequency. If I put that concert A on a tone generator or a pitch pipe, my husband on his phone has a pitch pipe because he has a very lovely tenor voice and has what he refers to as near perfect pitch. I think it's perfect pitch. He says it's near perfect pitch. He says there's a difference. After many years of arguing, I have discovered that maybe there really is a difference, and I will concede it. But for those of us who don't have it, it sounds awfully perfect to me. My son is right there with him. It's irritating. But they have what they call relative pitch, and they can nail a note. But the thing is between the oboe and the violin, they have something called timbre, and those are the overtones and the color of the music that you'll have. The overtones and the color come in. So timbre is going to be related to what is generating that tone. It's going to be related to what's generating that tone. I do have a slide. And that's going to be the quality and the mixture of the harmonics. So the resonant box in my violin is going to provide a different timbre than the resonant box in my oboe. And that's where the color of the sound is going to come from. So it's a characteristic that's related to those overtones and the mixtures of the harmonics dealt with in the resonance box. So we have timbre. So intensity is going to relate to loudness. Frequency relates to pitch. And timbre relates to the color and allows us to tell which one's which. We already talked about that. And I think that gets us through all that lovely chapter. So I'm going to switch over here. So Friday, what I'm going to do is make sure I've got everything kind of set up make sure Blackboard's all set up, make sure we've got all of that in there. I will make sure that we have places to put all 3 labs, the Doppler effect lab, the 1 over R squared lab, and the speed of sound lab. So those will be all in there together for you. I'll go ahead and probably issue a quiz, that way you see some types of questions before a test, because it's not necessarily fair to hit you with a test and you've never seen what kind of questions. So I'll get that kind of set up, and then on Friday we'll work some more problems, look at where we're at on problems, and then next week we will start with electrostatics, and I'll set up the test. So questions? Everybody good? All right, just a reminder, over in Enid, tomorrow I have a 2:30 meeting. If you can come in early, collect your data, great. You can also come in on Friday and collect your data. What does it take us, a whole grand total of about 10 minutes to collect data? Yeah, it didn't take much to collect this data. And I'll have it set up for you guys over in Enid. And so if there's any questions, holler, and I'll see people on Friday.